In this example, I want to do something that's a little bit different. So we're going to be dealing with concepts of proper time, proper length, and the Lorentz factor. All right. But in this case, what we're going to be doing is trying to find the speed. Okay. If we have some known quantities, how can we find the speed? All right. So let's set it up here. All right. So what I'm imagining is Earth is over here. Okay. Ooh, all right. And then way over here is a star system. There's a star called Alpha Centauri. All right. So I'm going to call it Alpha right there. And so there's some aliens that come from Alpha Centauri. All right. And of course, obviously, they're in a flying saucer. Okay. And they're traveling this way at some speed. Okay. All right. Now, we can look and see the distance to Alpha Centauri. Okay. Now, we're not measuring the size of Alpha Centauri. If we were measuring the size of Alpha Centauri, I mean, we could do that, but it's not going to be a proper length measurement of that size, okay, because it's moving and we're moving. You can't do that, okay? However, the distance to Alpha Centauri, we can get that, and that is a proper distance, okay? And it happens to be that that particular distance, all right, is, we got it written down here. There it is. 4.367 light years. I don't think we need the S on there. Okay, 4.367 light years. All right. Now that is a distance. Okay. Now you're going to see in science fiction movies and popular culture, people are going to screw that up. And they're going to represent it like it's a time or something like that. But it is actually a distance. And what it means is that it takes light 4.367 years to get from Alpha Centauri to the Earth. And of course, vice versa. All right. So that's kind of how that works. All right. Which is crazy. All right. We're going to talk about this a little bit later. But what that really means is when you're looking at the stars in the sky, okay, the light has been traveling for a long time. Okay. Decades, centuries, sometimes millions of years. Okay. And there's some measurements where it's in the billions. Okay. And so when we look into the stars, we're really looking backwards in time because we're not seeing the stars how they are. We're seeing them how they were. Okay. Seeing them how they were. So kind of imagine a little bit like a lightning strike. Okay. You see the lightning strike, but then it takes a little while to hear the thunder. Right? So it might take 3 or 4 seconds or something to hear the thunder. So that thunder you're hearing is from something that happened a few seconds earlier. Okay. But now these scales are so large, that's happening with light. Okay. So you look out there at an object, and it's a very long ways. In fact, light from the sun takes several minutes to get here. If the sun were to suddenly wink out in total darkness, it would be around 8 minutes or so before we noticed anything here on the Earth. Okay. Let's get back to our situation here. So that's a distance. That's how far that is. And that is the distance that we Earthlings record. Okay. All right. Now, it would be the same distance for people in Alpha Centauri who stayed on Alpha Centauri, okay? But we know, hint, hint, we know here that the aliens that are traveling to us, they're not going to experience that, okay? In fact, that right there is the proper time. And the aliens that are in transit will not experience that distance. Their distance will be shorter, okay? Well, the aliens land and everybody's happy, and we exchange gifts, we give them chocolates and whatever, and they give us something that looks revolting, but we accept it with pleasure. Okay. So that's how that would go. That's how that would go. Then we ask them, once we establish language, we can talk to them, we say, well, how much time did it take for you to get here from your planet. Okay. And they say that it took them, okay, so I'm going to put a little alpha on there for Alpha Centauri, half of a year. Okay. But you know how they do it in science fiction shows? 1/2 of your Earth years. Okay. So they tell us that 1/2 of your Earth years. All right. Very good. All right. So now we might want to be like, okay, so let's figure out how fast they went. Okay. And so we might just jump right into it and do this. We might jump right in here and say, oh, well, I know I'm looking for a speed. I need to obtain a length over delta t. And that's true. Length over delta t is going to do the trick. But it's got to be from the same perspective. Okay? In other words, we're going to need LE delta t E. How much time did we observe that it took the aliens to get here? Or it's going to have to be L alpha delta T alpha. Okay? It's going to have to be one of those. We know delta T alpha. What we don't know is L sub alpha. Okay? We don't know that guy. All right. So how are we going to do this? Okay, well, we have already talked about how this is the proper length. This happens to be the proper time. Okay, and again, think about it this way. When the aliens are on they're on their home world, the door closes, okay, they see Alpha Centauri, their planet there, and then the door opens and there's Earth. Okay, and they know how much time it took for the scenery to change. Ooh, Alpha Centauri. Ooh, Earth. All right. They didn't go anywhere in their reference frame. The universe went flying past them. Okay, went flying past them. So they have the proper time. Okay, so the easiest way to work through this is really to do this little trick right here. Okay, we're going to say that since they have the proper time, the Earth time is actually gamma times what they see. Okay, and what I want to do is I want to focus on this term here. All right, and let's do this right here. We're going to say LE delta T sub E. But I'm going to substitute in what we did just a second ago, gamma delta T alpha. Okay? And remember, what we're trying to find is the speed for the flying saucer. Okay? How fast was it going? And it might look like I'm in a pickle here, but remember, that velocity is buried in gamma. So I've actually got a velocity term in there. All right. So let's take this another little step here. All right. So this is going to be L sub E. Okay. And then we're going to have gamma. Gamma is 1 over the square root of 1 minus beta squared, like this. Okay. And then now we've got our delta T alpha in here. Okay, now I've got the 1 over in the denominator, so that brings it up to the numerator. Okay, so then I have 1 minus beta squared LE over delta T alpha. Okay. Okay, now it might still be a little confusing. You're like, wait a minute, where's the velocity? Remember that beta is V over C. Okay, it's V over C. So I tell you what, let's do this. Let's take V. We got V way over there on the left-hand side. And let's divide everything by C. Let's divide everything by C. Okay, and so what that means I'm going to get is I'm going to get V over C, and that's beta. But my V over C is LE over, I got to put a c down here, delta t alpha. Okay, and then I still need to have my square root of 1 minus beta squared term on there like that. Okay, but now the equation that I'm working with looks like this. Okay, it's looking like that. So at this point, it's all algebra. Okay, it's all algebra. And so what I'm going to do in order to sort of help me navigate that algebra is this term in the parentheses right here. Okay, I'm going to call that the Greek letter lowercase c. Okay, which looks like that. All right. And oftentimes we can refer to it as squiggle. Okay, so let me rewrite my equation. So now I have beta is equal to squiggle LE. Oh, no, that is my LE term. Sorry about that. I need my square root of 1 minus beta squared. Okay, so now I'm in a position I can begin to untangle this thing. All right, so I'm going to square the universe here. I get squiggle squared, 1 minus beta squared. Let's go ahead and distribute the squiggle. Okay, I can take it to the other side. Now I've got beta squared plus squiggle beta squared is squiggle squared. Pull out my beta squared term. 1 plus squiggle squared. Squiggle like that. Okay, and of course then that means that my beta squared term becomes squiggle squared over 1 plus squiggle squared. And so beta is going to be the square root of all that. Okay, so actually we can do it this way. Squiggle square root 1 plus squiggle squared. Boop. Okay, so if we knew the value for squiggle, then we'd be in good shape. Okay, and actually we can. Okay, so remember squiggle, what we've said is LE over C delta T alpha. Okay, now here's a cool thing that happens. All right, so I know some of you have been bothered from way back at the beginning when we talked about this thing being measured in light years. Okay, some of you guys were like, wait, what? What are we going to have to do with that? All right, check this out. Okay, this is pretty cool. This is pretty cool. How come I can't move my? There we go. Okay, so let's go ahead and put that in. So our distance there was 4.367 light years. And then we've got the speed of light, c. Okay, now I'm not going to put it in as meters per second. We're just going to leave it as c. Check this out. Put our delta t alpha, which also is weird units. Okay, half a year. All right, some of you maybe were wondering, why didn't we change? This should be a light year. Sorry about that. Light year. Why didn't we change that time into seconds? Okay, we could have done that. We could have changed L into a distance. We could have done that too. Okay, but look at this with our units. Years cancels, speed of light cancels. So now I just have a number, 4.367 over 0.5. So that means my squiggle term, all right, turns out to be 8.734. Okay, 8.734. So I can take that and I can dump it into this equation down here. Okay, so I'm going to have beta, got 8.734 divided by the square root of 1 plus 8.734 squared. And what I get for beta when we do that is 0.9935. Okay? So how fast are the aliens going? If beta is 0.9935, then that means that the alien craft is going 99.35% of the speed of light. Okay? 0.9935 C. Just like that. Okay? Now, if you want to convert that into meters, that's fine. It would depend on, if when your homework problems like this, then you'd have to say, okay, so what are my units? But you can see here by doing it as 0.9935 C, C can be in any units you want to. Okay? It could be in kiloparsecs per year. Okay? It could be in microns per millisecond. It doesn't matter. It doesn't matter what it is. Okay? We know that ratio is going to hold. So whatever units you want to use for C, fine. Use whatever you like. We got V now in those same units. Okay? So anyway, this one you can see not really a lot of relativity here. Once we established proper length and proper time, okay, then it's really just a matter of algebra, okay? And sometimes, to be really honest, there's just some kind of tricks that can make things easier. So I've tried to show you a couple of those tricks with the algebra here, all right? And mainly that is to embed things, okay? So I've got a velocity, turn my velocity to a beta. Now I've got all betas, okay? So that was trick number 1. Trick number 2 was using squiggle, all right? You can use whatever symbol you want to, okay? You don't have to use the Greek letter C. It's tricky, all right? But it's just so nerdy. It's just fun. It's just a fun substitution to make, all right? And C's not really used for anything else, so it's a good dummy. Okay, there you go, guys. There's a couple examples for you, so you should be well equipped for your homework then, okay? Figure out how to get out of this thing. There it is.